In the 1930s, vitamin research indicated that several vitamins, particularly vitamin A, absorb ultraviolet light. Spurred by the American government's interest in measuring vitamin content in soldiers' ration using ultraviolet and visible light, this research culminated in the commercial launch of UV-vis spectrophotometers in the early 1940s. UV-vis spectrometry refers to absorption spectroscopy or reflectance spectroscopy in the ultraviolet visible spectral region. This means it uses light in the visible and adjacent. The absorption or reflectance in the visible range directly affects the perceived color of the chemicals involved. In this region of electromagnetic spectrum, atoms and molecules undergo electronic transitions. The definition of UV-vis absorption spectroscopy ultraviolet is the measurement of the attenuation of a beam of light after it passes through a sample or after reflection from a sample surface. Absorption measurements can be at single wavelength or over an extended spectral range. Ultraviolet and visible light are energetic enough to promote outer electrons to higher energy levels, and UV-vis spectroscopy is usually applied to molecules or inorganic complexes in solution. The UV-vis spectra have broad features that are of limited use for sample identification, but are very useful for quantitative measurements. The concentration of an analyte in solution can be determined by measuring the absorbance at some wavelength and applying the Beer-Lambert law. The instrumentation of UV-vis spectral range is approximately 190 to 900 nanometers as defined by the working range of typical commercial UV-vis spectrophotometers. The short wavelength limit for simple UV-vis spectrometers is the absorption of ultraviolet wavelengths less than 180 nanometers by atmospheric gases. The long wavelength limit is usually determined by the wavelength response of the detector in the spectrometer.
First, press the power switch on the back. Wait for the instrument to finish self-check function. Let it warm up for at least 15 to 20 minutes to enter the desired mode. Open the sliding compartment of the UV-vis spectrometer. This will be our blank. And this will be our sample solution. On the sample compartment, we'll place a blank and the sample solution. Blank on 0 mark and sample on 1 mark. And close the compartment. On the menu, press the fixed wavelength. In our case, we'll change the 600 nanometer to 625 nanometer. And then press OK. Press the carousel option symbol. And press arrow down until the cell number reached 2 or until it shows blank 1, read 2, and press OK. Press blank and read and wait for the results. Now, let's go to wavelength scan. Press the 260 nanometer to access the wavelength range. Change the range to 450 nanometer and the 500 to 625 nanometer and press OK. So the interval is 450 to 625 at 1 nanometer per wavelength. Press blank and wait for the results. After blanking and reading, press cell 2 and press either table or graph. This time we'll press table first. Observe 450 nanometer until 625 nanometer. Now we'll see that the peak is 640 nanometer with its absorbances of 1.356. Again, press cell 2 and press graph. In here, the resulting graph will be shown. It shows the 625, which gives 640 nanometers and the 1.354 absorbances. Just like the table, the highest peak is 1.357 at 615 nanometer, which means this is the correct wavelength for the absorbances of the sample. This result reads the sample at the visible spectrum. Open the compartment and release the blank and sample solution. Close the compartment and turn off the power.
The application of UV-vis spectroscopy is routinely used in analytical chemistry for the quantitative determination of different analytes, such as transition metal ions, highly conjugated organic compounds, and biological macromolecules. Spectroscopic analysis is commonly carried out in solutions, but solids and gases may also be studied. With its principle that molecules containing non-bonding electrons can be absorbed the energy in the form of ultraviolet and visible light to excite these electrons to higher anti-bonding molecular orbitals. The more easily excited the electrons, the longer the wavelength of light it can absorb.